overview of what's called the collision theory of reactions. And basically then, it's kind of like a model that's been created that tries to explain, okay, why do reactions happen? And then once we kind of know the pieces that make a reaction happen, we try to figure out, okay, well, how can I tweak that reaction then to make it go faster or slower according to my needs? So one thing is obviously molecules have to actually collide in order for them to react. They can't just react if they're clear across the room from each other, right? They have to actually collide. And then when they do collide, they have to have sufficient energy so they can actually break apart the bonds in the reactants. So the reactants are already together, have to break them apart. That's the first piece. And I'll come back to each of these here in a little second. I'll spend a little more time on them. Then they have to collide the right way. They can't just connect any old way. They have to connect only in a certain orientation, kind of like Legos. You can only attach Legos if you attach them a certain way. You can't just put them all top to top or side to side. It's got to be a certain orientation. And the third one I'll mention is that when you break some bonds in the reactants, well, then you have to also make new bonds in the products. So there's three pieces. Like I said, I'll kind of briefly run through these. So they have to collide with sufficient energy, have to collide the right way, and they're not only breaking bonds, but we have to also make the new bonds. So let me just dive into these a little bit more. So the first one is, like I said, when they collide, they got to have enough energy to actually break apart those bonds. So for example, in this case, this is N2 and O2. Well, when they collide, they have enough energy to actually break apart the two N's and break apart the two O's. So they can't just kind of collide, kind of generally. You have to have enough energy to actually collide. And if they don't have that energy, well, they just bounce off each other. And the other thing is, pardon me, they have to collide the right way. So if my goal, like I showed you on that previous slide, for example, is to take an N2 and an O2, collide them, break these, and then reattach them into NOs, well, it has to happen a certain way. So it can't just happen, like you see here, if they collide end to end or end to side or things like that. So it also is the orientation is important. So that's enough. So you got to have a collision, but you got to have enough energy in the collision, and you got to have the right orientation when they collide. Again, it's kind of like Legos. You can't just collide, but you got to actually collide them the right way, and you have to snap them together then with enough force to actually kind of stick. Does that make sense? You have to have enough energy and the right orientation. Okay, so that's kind of the first piece. So whenever a reaction goes from reactants or to products, there is this amount of energy then that is being required to get from reactants to products. Again, it's that energy then that's required for them to actually break apart the bonds and such. Well, that amount of energy is called the activation energy. So once you get that amount of energy, then you have now then activated the reaction and it can start going forward. So we typically abbreviate that as E, the little lowercase a, by the way, activation energy. So it's not just like, okay, well, the energy is over here for the reactants. Here's their potential energy. Here's the product's potential energy. It's not just a straight line between the two. There is a barrier, again, like I said, a hill you have to climb in a sense. And once you get over that energy, then it's all downhill and the reaction can go. It's got to have at least that amount of energy. Like a roller coaster in that sense. Okay, well, once a reaction goes, as I mentioned earlier, how about the speed of that reaction? Well, how fast is it going to occur? So you can measure the rate of a reaction just the way you can measure the rate or the velocity of anything. Okay, well, how fast is it changing per time? So, for example, like in your car, right? Measure the rate of travel. Well, it's change in miles per hour, right? The change per time. Well, for a reaction, then we're going to measure what's changing is the concentration. So you can either measure the rate at which the reactants are being used up and turned into products per time, or you can measure the rate at which you're making the products. So you can measure it either way. How fast are reactants being used up, or how fast are products being produced. You can do it either way. Gives you the same kind of thing. Because you can't have one without the other. So again, just a rate. Like I said, like miles per hour, but ours is going to be molarity per second, or whatever it's going to be. That makes sense? Or molarity per hour, or molarity per minute. Just change the concentration per time. Okay? So there are a few ways then that we can try to affect the rate. So we know that we want, generally, then, for a fast reaction, you want more collisions and you want harder collisions. So one thing we can do then is we can change the temperature. We can make it hotter or colder. So which way then will give us more collisions? Hotter. Why?
More kinetic energy.
Yes, exactly. So when you heat things up then, give them more energy, which means they move faster, so they're going to collide more often. And when they do collide, they're going to have more energy in that collision at the same time, right? So yes, if you increase the temperature, you can generally speed up a reaction. And the opposite is true as well. If you were to cool them off, well, they'll move slower. They'll move slower then, so they won't collide as often, and they won't collide as hard. So you're going to slow down the reactions, okay? The other thing you can do is you can change the concentration. So you can take a reaction, and maybe it's only, I don't know, it's only 1 molar in the reactants. Well, if I suddenly make it 10 molar, and I put in 10 times as many molecules, that will make the reaction faster. Why would that make it faster? If I increase the concentration?
It's more likely for them to collide because there's more of them.
Exactly, yes, so more collisions, right? So there's 10 times as many, so we're going to have 10 times as many collisions, right? So more collisions, and every time they collide is opportunity for them to collide the right way with enough energy and everything like that. The third thing we can do is we can add what's called a catalyst. Okay, so let's just talk about each of these real briefly. I already gave you the broad strokes, but first thing, temperature change. So like we just said, if you heat things up, that means you're going to increase the amount of kinetic energy, which means they're going to move faster, and they're also going to have more energy when they collide. So you're going to have more collisions, and you're going to have harder collisions, right? So that's more likely then for you to be able to hit hard enough to actually break apart the reactants and start that reaction, right? So that's a good thing. And then vice versa, right? If you cool things off, slower collisions, you're going to slow down the reaction. And I have a little note here, which is why you put perishable items in your refrigerator, because you want to slow down the reactions then that causes food to spoil, right? So they're not going to react as fast and rot and go nasty and mold on you as fast, right? So just the opposite is true. So yeah, so hot, faster, more collisions, harder collisions drive the reaction. And the opposite is true too. So you can cool things off, you can slow down reactions if you need to. Okay, another thing, okay, I just you can saw that. Whoa, whoops. Oh yeah, okay, and concentration, I already said that one, right? So if you have concentration, and you have 1 molar, but now I make 10 molar, right? So I have 10 times as 10 minutes of reactants. Well, again, just more molecules is more opportunity to have collisions. And again, every time they collide, there's a chance that they're colliding, hitting the right way and with enough energy. And vice versa, then, right? If you were to lower the concentration, where you're going to have fewer collisions, you're going to slow down the reaction. Now, the third piece is this thing called a catalyst. And a catalyst is interesting, and what it does is it speeds up the reaction. And the way it does that is it actually creates a new pathway between the reactants and the products. So it's no longer just straight A and B go to C and D. It has a new little pathway. And that new pathway actually drops that barrier, that little hill to climb. It makes that little hill there lower. The activation energy gets smaller. So you have a smaller hill for you to climb. Now, the interesting thing about a catalyst is it's not a reactant and it's not a product. It is not actually even consumed in the reaction. So you put in the catalyst and it's there when the reaction starts. It's there when the reaction gets done. It's not consumed during the reaction. Okay, so catalysts are not consumed in the reaction. So you put it in there, and all it does basically then is just to help the reactants to turn into products. Helps reactants turn into products. Help reactants turn into products. And does it over and over. But it itself is not actually used up or consumed during the reaction. There's all kinds of examples of these. Okay. Typically, then the way it does that, I won't go into all the logistics of that, but typically, basically the way it happens is it basically tries to coordinate things and makes it easier for reactant A to find reactant B. So not just like wandering around a beaker, it kind of brings them together. And then it also then tries to bring them together and make sure then they can connect the right orientation too, based off different things. But again, there's all kinds of factors. There's entire classes on this kind of stuff called catalysts. But the kind, though, that we've all heard of probably are enzymes, which are basically just nature's versions of catalysts. So an enzyme is basically present in your body to try to take a reaction that would not normally occur in your body at normal body temperatures and concentrations and actually make it viable. Because you can't just take your body and just speed it up by heating up your body 100 degrees, right? Because that would kill you, right? So you can't do that. So instead what we need then are we need catalysts that can take a reaction that normally has a really big barrier. You would need lots of heat and drop that barrier, and that now it can happen real easily then at our normal body temperature, 37 degrees Celsius or whatever it is roughly. Okay? So there's lots of these. Your body is full of all kinds of different enzymes. They are very amazing. Well, so most enzymes then, they only do one thing. They'll have one reaction then. They'll have one reaction then that is their job to help speed it along. But they do that one thing crazy well, as I'll show you. I mean, it is ridiculous how fast they can actually process through reactants. So I'll give you a few examples of some common enzymes you may have heard of at some point, or even not, or even if you have actually heard of them, you may have at least heard of their effects. So one is sucrase. So sucrase is a enzyme, and its job is to help catalyze sucrose, break it apart in your body so you can use it, and turns it into glucose and fructose. Well, so normally then in your body, it's much more difficult for your body to actually break down sugars into glucose and fructose. But sucrase makes it super easy, and it does this exact thing. But then on the enzyme, it has like a little sucrose-shaped hole, basically, and it pulls in the sucrose, and then it kind of takes it, twists it, breaks it apart, and spits out the fructose and the glucose. Sometimes this is called like a lock and key mechanism. If you've ever had a bio class, I've heard that term before, a lock and key mechanism, where your enzyme basically has an active site, and it pulls in the little sucrose, breaks it apart, spits out glucose and fructose. Pulls it in, breaks it apart, spits it out. Pulls it in, breaks it out, spits it out. But again, like I said, so it itself is not being used up, right? So all it's doing is just helping the reactants turn into products, but it's not being used. You can use it over and over again. Okay. So like I said, so basically on sucrase, there is a sucrose-shaped hole called the active site. Comes in there, and it does its magic. It helps to break it apart into glucose and fructose. Now some other ones. One is lactase. So this is present in most people's bodies and helps you to break down lactose. But if you are what is called lactose intolerant, then you do not have lactase in your body, and it becomes very difficult for you to break down all that spicy milk. You just can't handle it. I'm just kidding. But that's called lactase, because that takes in the lactose and it breaks it apart really easily. But if you don't have that enzyme, then again, like I said, it's much harder for your body then to break it down. So that's another enzyme, lactase. So sucrase, you know, they all end in A's. Sucrase, now lactase. Another very important one is called peroxidase. There's a whole set of these peroxidases, and these basically break down peroxides because your body is either manufacturing peroxides as byproducts, or you're accidentally just kind of ingesting them, and they are highly toxic. But no problem, because peroxidases go to work, find those peroxides, break them down, neutralize them, no problem. And again, they're very good at what they do, so they can do it. I mean, like in millionths of a second. I mean, boom, it's gone. So peroxidases. Now, another one is called, here's a big long name, acetaldehyde dehydrogenase. And acetaldehyde dehydrogenase is one that many Asian people are lacking. My wife's Korean, and she has the lack of this enzyme. So whenever she has a beer or a glass of wine, her face gets like bright red. It gets like really, really hot because she lacks this enzyme. She just cannot break down alcohol as easily as most people can. Because normally then what happens in your body is you have a beer or wine or whatever, and the ethanol then is broken down through a series of steps. And one of the breakdown steps is to make it into this stuff, acetaldehyde. Most people's bodies, like I said, just break that stuff down and go on, no problem. But in her case, she can't do that, so the acetaldehyde builds up. Like I said, it makes your skin all red and flush looking, gets you really hot. I've seen that before, like in people like that, they have, they get their face really red after a beer or two. So that's another one. Another one that was very important back in World War I and World War II is this one, acetylcholinesterase. So again, if you ever had a biology class, you might have heard of these things called neurotransmitters. So in your body then, what you have these little nerve synapses. And the way that messages are being sent in your body is on one side then is your nerve transmitter, and the other side of the gap is the nerve receptor. And the way a message is sent is it makes this stuff here called acetylcholine. Because you spit out acetylcholine, travels across, sends a message, tells your arm to flex out, or your fingers to bend, or your heart to beat, or whatever it tells your body to do, right? Sending those messages. But once the message is sent, once the message is sent, you have to break that stuff down. Else it'll just keep sending that message over and over. So you just want to send it one time, break it down, then you send a new message. Well, back in World War I, especially in World War II, all kinds of like chemical warfare agents and nerve agents that were basically built. And what these nerve agents would do, they would basically bind up and block acetylcholinesterase, and then it wasn't able then to break down neurotransmitters in your body. So what happens then in your body is your body sends signals for your arms to flex, or your legs to move, or your heart to beat, and it keeps sending that over and over, and it never stops sending that message, and you just, flex, seize, have horrible seizures, and you die. That's another enzyme. It gets a biological catalyst. And the last, but this stuff is normally insanely efficient. So it has what's called a turnover rate of 7.4 times 10 to the fifth molecules a second. So that's 740,000 times a minute. So what that means is in a minute, one of these little enzymes can process and take in 740,000 of these acetylcholines, break them apart, and spit them out. So think about that. 740,000 times every minute it can do that. So if you were to do that in a second, divide that by 60, it'd be what? About 12,000 times a second? So imagine, it pulls one in, breaks it apart, spits it out. Does that 12,000 times every second. 12,000 times in a second. Is that insane or what? So like I said, these enzymes, they are finely tuned to do one job, and they do it better than anybody else, right? So they just pull them in and spit them out, pull them in and spit them out, pull them in and spit them out, 12,000 times a second. It's crazy. Okay. So again, catalyst, they lower the activation energy, but they're not actually used up, right? So they're not reactants, they're not products. Okay, so let's just kind of quickly predict a few of these, and you tell me. Okay, so A, B, C, D, and E, if I were to apply one of these stresses, would that increase the speed, the rate of the reaction? Would it decrease it, or would it not have any effect whatsoever? So pull out your handout, take a guess, real quick. Write down your 5 guesses. Write down real quick. Increase, decrease, no change. You can take your 5 guesses, and then we'll discuss with the neighbor. So write down your 5 guesses first, and then we'll compare with the neighbor. Okay, so once you both have 5 guesses, find somebody and talk it over. And if you don't agree, well, rationalize it together. Yeah.
Like all the examples of enzymes that we were giving, there seems to be issues with lack of enzymes, but like if there's like too many enzymes, that could be an issue as well. Like if when you get your liver tested and they say your enzymes are too high.
Right. Yeah.
As like a different reaction.
Yeah, I have heard of it. I don't know what the reason is,
Yeah.
or what the danger is, I guess, from too many enzymes.
I think like when it reaches a certain point, then
Maybe it breaks.
psoriasis is
Maybe it breaks down too many things, so you can't actually get that health benefits out of it. Maybe, I don't know. I don't know why that is. That's a very good question. Okay, would you compare yet? Your 5 guesses. Find somebody. Okay. So if you heat it up, if you increase it, will that make it increase the speed, decrease the speed, or no effect? It'll increase the speed, right? Oh, because what if you remove out some of the reactants? So you decrease the concentration, in other words, right? You pull out some reactants. Well, fewer collisions then, so you're going to decrease, right? How about the next one? You add a catalyst in there. Makes it go faster, right? A lot faster generally. Okay, how about the next one? Now you take your flask and you put it in some ice. Again, move slower, easier collision, so decreases. And the last one, you increase the amount of the reactant now. Okay, increase. Okay, I think we got that right.
What would be a no change?
If you add something that's not a reactant or a product, like you just, I don't know, you take a whiz in your beaker or something, whatever. Yeah, that won't have any effect whatsoever, or something like that. Okay, well, I'm going to skip number 2 because I think you got that. Change the temperature, right? Add some of this, remove some of that. Okay, well, now we've kind of lied to you in the book so far, and we've been writing reactions mostly up to now with a single little arrow like A plus B go to C plus D. But most reactions do not actually go 100% all the way. And I mentioned this briefly in the lab last week with what are called like weak electrolytes, remember, and weak acids. So actually most of the time that's actually what happens. Most reactions are actually what are called reversible. And reactants do go to products, but products can also go back to reactants. It is a two-way street. So we're going to start writing this kind of a little arrow like this, like a little double half arrow, pointing in both directions. Because most reactions are actually like that. There are very few reactions that actually go only to products, and you can't undo it. Most things are a two-way street, at least mildly. So this is called an equilibrium arrow. It's like a little double harpoon there. So that's the way most reactions actually are. They are reversible. So yes, you can turn A and B into C. You also turn C and D back into A and B. So let's just kind of think about this for a second in terms of the rate of the reaction. So let's just say we have a reaction to make up A plus B goes to C plus D here. So when I first have my beaker, I dump in A and B begin to react. So at first, it's only happening in the forward direction, right? There's only A and B to react when you first start the reaction, right? There is no C and D yet. That makes sense. You haven't made any C and D yet. So at first, A and B get used up and go to C and D. A and B makes C and D. A and B makes C and D. But over time, though, what happens? Over time, the A's and B's then are being used up and turning them into C and D, right? So as they're being used up, there's fewer of them, which means what happens to the rate? It's going to get slower. So initially what happens then is you have the maximum amount, and then as you use them up, it gets slower and slower and slower and slower. But then over time, as A and B begins to turn to C and D, well, now they're swimming around, and C's trying to find a D. So a C finds a D and goes back. And a C finds a D and it goes back. So that one at first, like I said, there is no reverse reaction at first because there is no C and D. But that one kind of picks up speed. As you make more and more of it, well, now it's easier and easier for a C to find a D. And easier for a C to find a D. Until you get to this point, which we call equilibrium, where the rate of the forward reaction, A and B going to C and D, is equal to the rate of the reverse reaction, C and D going to A and B. So that is called equilibrium, when the rate of the forward reaction is equal to the rate of the reverse reaction. Okay. So that's equilibrium. So let me give you an example. So let's say H2 plus I2 is an equilibrium with 2HI. So you get equilibrium when the rate of the forward reaction is equal to the rate of the reverse reaction. So let's say at first you dump in H2 and I2. Okay, boom, you dump it in there. So you show this little picture here. We have 4 hydrogens and 4 iodines. So we have 8 total molecules, right? Bouncing around. Well, over time, a hydrogen and an iodine, they collide, and they spit out 2 HIs. So here it was 8 reactants and no products. So it's very fast in the forward direction. Well, now we've done some of that, so now we only have 6 and 2. So now the forward reaction gets a little slower, because there's less of the reactants there, right? Does that make sense? So it's harder now for a hydrogen to find an iodine, because there were 4 of each, now there's only 3 of each. So it gets slower. But now there's 2 of these HI swimming around, right? So they can find each other and go back to H2 and I2. Does that make sense? Well, the eventually, like I said, is it keeps happening, until you reach whatever that point is, where the rate of the hydrogen and iodine turning into HI is the same as the rate at which the HIs are turning back into hydrogen and iodine. So that's the equilibrium. When the rate forward is the same as the rate reverse. Does that make sense?
So how do you know when it's equal?
Okay, good question. What you have to do then, you have to measure then the concentration. You have to measure the amount of hydrogen that's in there, the amount of HI that's in there, whatever. And once those have stopped changing, and they're constant, then you know you must have reached the equilibrium. Well, so equilibrium does not mean that the amounts are equal. All that it means is that the rate from forward and the rate to reverse is equal. Okay, so it doesn't mean it's like perfectly even and it's 4 and 4. It doesn't mean that. It just means the rate at which these are turning into that is the same as the rate at which these are turning into that. So that's the same rate going back and forth. So that's equilibrium. Awesome. Okay. So one nice thing then we can learn to write is what's called an equilibrium expression. So you can take a generic reaction like this, A plus B goes to C plus D. And I'm going to write what's called an equilibrium expression or an equilibrium constant. And basically then what this is going to show is, okay, so what is that ratio? What is the concentration of the products compared to the reactants when I reach that nice balance point, when everything's happy? So I just literally write like this, a big capital K, and you may see it called KEQ, which or basically call, KC, and C is for concentration. But basically it is okay, once I've reached that steady state where the reactants are turning into products and the products are turning into reactants at the same rate, what are those concentrations? So all I do is I take the ratio of the products on top over the ratio of the reactants on bottom. Now you'll notice I've written these with little square brackets. See this little square bracket C. So that means the square brackets means the molar concentration or the molarity. So the molar concentration, the molarity of C to the C power times the molarity of D to the little d power over reactants. Molarity of A to the A power, molarity of B to the B power. So these little lowercase letters, those are the coefficients out front. You know, the 1, the 2, the 3 we put out front of those things when you balance reactions. So if it was, 2 HIs, it'd be HI, and I put the 2, I'd square it. If it was 1 H2, it'd be H2. So those little lowercase are the way we balance it. Remember those 1s, 2s, 3s you put to balance it. So again, it is a square bracket, and square bracket means molarity, or means molar concentration. Okay, square bracket means molarity. Okay, so let's just try an example. How do I name this, by the way? 2 of these things. How would you name that? Dinitrogen pentaoxide go to 4 nitrogen dioxides and an oxygen. Okay, so if I wanted to write the equilibrium expression, again, you might call it KEQ, you might call it KC. You'll see it both ways depending on your textbook. We're going to write the ratio of the products over the reactants. So my products. My first product is NO2, so I'm going to put square bracket. The concentration of NO2, and then as an exponent, I'm going to put that coefficient that was with the NO2. So it's 4 NO2s, so it's concentration of NO2 to the 4th power, times the next product, concentration of O2. And there's just a 1, so I didn't put anything in there, over the reactants. Concentration N2O5. And there was 2 of those, so I'm going to put that to the 2nd power, so squared. See how that works? So yeah, so once we've reached the equilibrium, like I said, you basically just kind of take a snapshot and say, okay, so what are these concentrations? And then you can find this constant here. And I'll come back and I'll show you a little more about some numbers with that here in a second. But first let's kind of practice Just kind of writing a few of these. So let's look at the first one. So, okay, let's write A together. N2 plus O2 goes to 2 NOs. So, okay, again, EQ or C, your choice. Well, what's going to go on top? Concentration of which of those three? NO. Yes, squared, right? Because of that 2 right there. Over what? Concentration of N2. Okay, and concentration of O2. Right. So again, square brackets. All right, it's not parentheses, square brackets. Okay. Awesome. Okay, your turn. Try the next couple on your worksheet there. Try B and C. Okay, let's compare with the neighbor. What's your right? Okay, do you agree? The neighbor? So you should have got concentration of NO2 squared over concentration of N2O4, right? Okay. Next one, try that one real quick. Well, compare whenever you get a chance, or whenever you get done. Okay, so we should have got concentration of silicon tetrachloride, SiCl4, times concentration of hydrogen squared, right, over concentration of SiH4 times concentration of Cl2 squared, right? Okay, so again, so this constant basically measures the ratio of the change in the products versus the reactants. Now, one interesting little thing about this is we're not going to include pure solids or pure liquids in this constant because you cannot change the concentration of a pure solid or a pure liquid. So I'll give you an example. Let's draw a little beaker here. So this is my beaker, and in my beaker I have some water. So here's my water. So concentration is the amount per volume, right? Like moles per liter or things like that, right? The amount per volume. So if that's pure water, that's a pure liquid, I cannot change that water and make it more concentrated. I can't now make it waterier water. It's already as watery as it's going to get. I cannot take that volume and cram more water into it. Does that make sense? I cannot increase the concentration of water. The only way then to increase the amount of water is to also have more volume of water. Does that make sense? So again, like I said, I can't make water less concentrated. I can't make water more concentrated. It's always a set amount because again, it's already packed in there as tight as it can be, right? So all the molecules are already packed in there. There's no room to cram more into the same volume, right? So I'd have to increase the volume, which would also then correspondingly increase the amount. So it's a set ratio of amount per volume. Same thing with solids. So if I have a solid, I don't know, let's say it's sodium chloride. I have sodium chloride, and it's a whole bunch of chlorines in here, all packed in. I'll make my chlorines green, for example. Let's say my sodiums are blue, whatever. Well, again, they're all packed in there, right? They're button heads. I cannot increase the concentration. I can't make it saltier salt. Are you with me? I cannot cram more into that same space and make it more concentrated. Does that make sense? The only way then for me to get more salt is to also have a bigger volume of salt, right? So that ratio of the amount per volume, that concentration, is the same. But I can change the concentration, let's say, of salt water. So let's say salt again is green. So salt water, yes, I could have water, and I could dump in more salt into my water and dissolve more salt and change that concentration, right? So I can make saltier water, or I can make stronger coffee, right? So things like that are aqueous solutions, those work just fine because you can vary the amount. You're really quiet. Does that make sense or not? Are you sure? Okay. Gas is the same way. Gases, then I can also change the concentration, right? So if I have a box and I have some gas bouncing around in here, okay, well, that gas has a certain concentration. Well, I can totally change the amount without changing the volume, right? So I could totally pump in some more gas and change that concentration, right? I could pump in some more gas, change that concentration without changing the volume. Or the reverse is true as well, right? I could go back and I could begin to remove some of these, right? And lower the concentration. So gases and aqueous, those you can include all day long because those you can change the concentration of. But do not include solids or liquids. So in this case, calcium carbonate solid goes to calcium oxide solid and carbon dioxide. So the K is just concentration of carbon dioxide. I don't include solids. I don't include liquid concentrations because those concentrations are always constant. Okay. How about this one? Lead 2 chloride, you put it into water, and it does dissolve just a little tiny bit. It's basically insoluble, as you know from your solubility rules. But a little bit of it dissolves and makes lead 2 ions and 2 chloride ions. Well, how do I write the K for that? Well, it would be products over reactants. So I would put concentration of lead 2 times concentration of chloride squared, and then that I wouldn't even include, right?
Probably over anything.
Nope. I mean, it'd be like 1, I guess. But yeah, nothing there because it's constant. And so basically, don't include solids or liquids. That's the rule of thumb. Aqueous gases, those are fine. Don't include solids or liquids because you can't change those concentrations. Okay, let's try one. Write the equilibrium expression for that one. Again, KEQ or KC, call it either one. Products over reactants. Okay, so, oops. So tell me here what you got. Concentration of what over what? CO squared over CO2, right? Yeah, and don't include the solid, right? Okay. How about that one? Try that one. Okay, so this one, what'd you get? Concentration of what on top? CO2. Okay, anything else? Over concentration of CO, right. So again, we don't, awesome, okay. How about that one? Okay, again, don't include liquids, right? So just concentration of CO2 over concentration of PCl5. Okay. Let's jump down and do this one. Let's do E. Because that one just takes a little thinking. Okay, so how would you write that one? What do you think you would do? Yep, so nothing on top, so we're going to put 1. You're exactly right. Good job. 1 over O2 cubed. Okay, so it's not 0, by the way. It's just put a 1. Yep, so you don't include that solid or that solid, so all you include is the gas. So you have to be 1 over O2 and the cube because of the 3 exponent. All right, moving right along. Easiest chapter ever. Okay. Okay, well, let's take some of these K and let's just try to calculate an actual number for this. So like you asked, Lauren, okay, so how do you know when it's happened? Well, what you do, like I said, you measure the concentrations and you see what they're at. And once they've stopped changing, then you know you've reached equilibrium. So let's say that happened and we measured the concentrations and the hydrogen was 0.11, the iodine was 0.11, and the hydrogen on iodide was 0.78. So what's the actual value for the K? So first I got to write the K expression. So I'm going to write K, oops, try this one, Kc equals concentration of Hi squared, right, over concentration of hydrogen times concentration of iodine, right? Right? That all makes sense, right? You take that reaction and Hi squared over H2I2. Okay, so now we're going to plug in the values. So the value for Hi, it was 0.78. And you can use square brackets or you can just use parentheses or whatever you want to use for this part. But it's a molarity, and it's squared, right? So don't forget the 2, because it was squared, over concentration of 0.11 times 0.11, because they're both the same. So we plug those in our calculator, and we punch them in. Looks like they're going to be 2 sig figs, whatever it is. So 0.78 squared over 0.11 squared, basically. So what would it be with 2 sig figs? So 2 sig figs have to put either a decimal at the end, or I could do 5.0 times 10 to the 1. Okay, so one little note for these. Equilibrium constants don't have units. There's never units on these. They are just purely a ratio of products to reactants. So I'll say that again. No units on equilibrium constants. Do not include units on equilibrium constants. No units on equilibrium constants. So it's not like, oh, molarity squared over molarity leaves molarity or whatever. Nope. No units on these. Awesome. Okay. Let's try this one together, and then I'll give you a couple to try on your own. So let's say the concentration of COF2 is 0.255, CF4 is 0.118, and the KEQ is given to me up here as 2.00. What is the CO2 concentration? So now we're going to find one of the missing concentrations. So let's write what we know. The Kc would be concentration of what over what? Concentration of what? CO2, good. Okay. Times concentration of CF4. Okay, good. Keep going. Over COF2 squared, right? Okay, so our mission is to try to rearrange and solve for CO2. So you can either go ahead and rearrange it first and then plug in, or you can plug it in first and then solve whatever is easier for you. Makes no difference. I'll just plug it in first. Why not? So 2.00 equals CO2 times CF4 was 0.118 over COF2, 0.255 squared, don't forget. So then you do a little algebra, solve for that CO2 however you do, and tell me what you get when you rearrange and solve for CO2. Make sure you can do that algebra. So we got to bring this up here, and bring this down here, or else do it all together first and then bring it all over. But somehow, just try that out. Make sure you can get that. Okay, try that out. Make sure you can do that algebra. So what'd you get for concentration of CO2? So this winds up going on top, right? This winds up going on the bottom, right? You do all that algebra. So what'd you get? Anybody? 1.10. Okay, anybody else? It's okay to be wrong. At least try. Then you'll know whether or not you were getting it or not. Something different? Same? What? Different or same? Same, 1.10. Okay, let me write out the math here because you're. So we had 2.00, right? So we have to bring up the 0.255 squared, right? And put the 0.118 down here, basically, is how it's working, right? So 1.10 Did y'all get that? Awesome. Okay. Oh, that one, by the way, was a concentration. So that one was molarity. I had it here, but have your capital M with your line under it. So that one does have here because that's a concentration. So put molarity on that. 1.10 molar. Okay, your turn. Try this one. Given these values for the concentrations, what would the value for the K be, the equilibrium constant? So write your K, plug in all your values, multiply it out, compare with your neighbor. Talk it over if you haven't. Compare with somebody. What's your units? What's your sig figs? Okay, what'd you get? What's the value for K? 66? Okay, let's try it out here. So concentration of CO times concentration of H2 cubed over concentration of CH4 over concentration of H2O. So I'm going to take the CO, 0.81, that was really messy, times H2 is 0.28, but that one's cubed, over CH4 is 0.13, and H2O, 0.53. And you got 66, you said, right? 0.26. Okay. I don't know, buddy. And you cubed the 0.28, right? Did you get 0.26 or 66? 0.26. Okay, so whoever got 66, go back and double check it. Let's make sure. I heard several people say 66. Make sure you cube the 0.28, you divide it by 0.13 and divide it by 0.53. Maybe you put your numbers in the wrong place or something. Everybody getting 0.26 now? Okay.
I still got 66.
Okay.
I still got 66 too.
Okay, don't use E. E is not exponent key. You want to use this for your exponent key?
Mm-hmm.
Oh, we got an error. What's going on there? Oh, I had extras. There you go, 0.26. E is the anti-natural log.
Yeah.
So
that's
you
what I was
use
doing.
this to the third.
Okay.
Okay, yeah, one issue was when you're doing that exponent, that cubed, you're going to have to use a key that looks like this to the third, or sometimes it's x to the y to the third, but don't use this key, the e to the x, because that's the anti-natural log. Don't use that key. Okay, let's try another variation. So here's a reaction. The K is giving to you as 680. They give you the SO2. They give you the O2. They say, find the SO3. So you got to do a little algebra here, too. Figure out how to isolate that SO3 concentration. Okay, help each other out. Okay, let's work it out here together. So we're going to write the K first. So the K is the concentration of SO3 squared over concentration SO2 squared over concentration O2. So let's plug in what we know. So 680 equals concentration SO3 squared over, let's see, SO2 was 0.300, O2 was 0.150. So I'll grab my calculator. Oh, wait, 0.300 squared, sorry. Squared, just square that.
Have to square the answer.
Eventually, yes. So that bottom part gave me 0.0135. So then I multiply both sides by that, right? So I get SO3 squared equals 680 times that. 9.18. And yes, now to get rid of that square, what do? Well, yes, I do square root of both sides to get rid of that, right? So I have to do square root of both sides. That gets rid of the square, right? I think it's like 3.03 or something, I think, or 3 points. Okay, follow along there. Okay. Okay, yeah, I mean, it's really not too hard. Just a little bit of algebra in there. The chemistry is not hard. Just plug in the numbers and solve for the variable. So, awesome. Okay. Like I said, K is the ratio of products to reactants. So let's think about, okay, what's the significance of that number? If it's really big or really small, what does that tell you about that reaction? So let's look at this reaction. Hydrogen and bromine go to make hydrogen bromide. So if I were going to write the K expression, I would write concentration of HBr squared over concentration of hydrogen times bromine. So if that number is 1.9 times 10 to the 19th, that is a huge number, right? That's a big number. So what does that tell you? Is there mostly products or mostly reactants? That number is really big. Which number has to be big? Is the top number really big or is the bottom number really big? The top has to be really big, right? If this number is really big, right? A big number over a small number gives you a big number. A small number over a big number will give you a small number. Right? If you divide by a big number, you get a small number. That makes sense? So this tells me, oh, if K is really large, that means it is favoring the forward reaction, and we mostly have products. So it means we're favoring the forward reaction. We have a lot of products. So when K is large, I'll say the third time, we are favoring the forward reaction, and we have mostly products. How about the reverse of that? Let's say we have K is a really small number. So for example, N2 plus O2 goes to 2NO. You measure the ratio of products to reactants, and it's 4.1 times 10 to the negative 31. So that's, 0.000030 times 4.1. Super small number. Oh, well, if it's a really small number, that tells me I must be dividing by a really big number. So NO squared over N2O2. And that it gives me a really small number. So that means I must be dividing by a really big number if I'm getting a small number out. Does that make sense? Right?
Yes.
Some of you say yes, some of you are just kind of staring at me. Right? So if it's 1 over a million, 1 divided by a million gives me a small number. A million divided by 1 gives me a big number, right? So this has to be the big number, the reactant. So that tells me, oh, it's favoring the reverse reaction, and I mostly have reactants. Right? So that tells me it's favoring the reverse reaction, and I mostly have reactants. So if K is large, it's going to products, making lots of products. If K is small, it's staying over here, the reactant side, making mostly reactants. Okay. Awesome. I think you got it. So real quickly, if it's really small, favors the reverse. What if it's about 1? Oh, that means the products and the reactants are about the same, and they're canceling, giving you 1. So it's not really favoring either direction, right? And if it's really big, then it's forward reaction favoring products. Okay, that's kind of the 3 possible cases. Okay, 15 minutes. We're doing great. Okay, let's wrap it up here. So, just real quickly, tell me, what do you think about this first one? 1 times 10 to the 95th. That is a big number. So does that mean I have mostly reactants or mostly products? Yes, it's gone way towards products, right? So it's almost all HF and very little of it's actually H2 and F2, right? How about the other one? 10 negative 7. Oh, that's a small number, right? 0.00000001. So I must be dividing by a big number, so I must have mostly reactants, right? Okay, good. Perfect. Okay, last topic here. Our new little French friend, the Chatelier. So the Chatelier's principle is kind of fun. It basically says that when you have a reaction and it's at equilibrium, because it's achieved this nice balance where the rate forward is the same as the rate reverse, it's not really changing concentrations, and then you somehow you tweak it, you disturb it, well, the system is going to react. And it's always going to react in such a way as to try to minimize the disturbance and get back to equilibrium. So you have a reaction and it's steady, and then I do something to it. So I take it and I add in some extra reactant, or I heat it up, or I somehow, like I said, I screw with it. Okay, it's going to try to react and get back to equilibrium and minimize that disturbance. Whoops, what happened there? So let's look here at this reaction. N2O4 is at equilibrium with 2 NO2s. N2O4 equilibrium with 2 NO2s. So write that reaction down there. So I had this reaction, and I wait a little while, and I wait for it to settle down and achieve a nice equilibrium. So the N2O4 is breaking up into NO2s. NO2s are reforming back to N2O4. It's nice and happy. It's just a nice little cycle here, going back and forth, and then I come along and I screw with it. So I come along now, and I suddenly pump in, and I add a bunch of extra N2O4. Whoa, the balance just went all crazy, right? So it was a nice, happy balance, and I threw it out of whack. Well, how can this reaction react? And what can it do then, basically, in order to try to compensate for all of the extra N2O4 I have on this side? Well, the way to get rid of the N2O4 is to begin to shift to the right and gobble it up and turn it into NO2. So in this case, then the reaction, if I added a reactant, it would shift to the right, because that's the way you can use up a reactant, is turn more of it into NO2. So in a sense, kind of like a balance. You have a balance here. It was nice and balanced, and now I added a bunch of N2O4. I'm like, whoa, it's all out of whack now. So how do I get it back into balance? Well, I need to use up some of this and make some more of this, right? So I have to shift that way to use this up and turn it into the products and get it back into balance. Does that kind of make sense? So that's all we're doing. It's trying to get it back into that equilibrium phase it has, which is not technically balanced, but you get the idea, right? I'll go for the metaphor there. Okay, so if I add N2O4, I'm going to shift to the right. Okay. What if I do the opposite? I come along now and I add in NO2. Now it's like, whoop, what's going on? Way too many products. How do I use up products? Oh, it's going to shift now to the left, which will use up some of that NO2 and turn it into N2O4 over here. Okay. How about just the opposite? Let's say I come in and I remove N2O4. I come in and I suck out a bunch of N2O4. Now there's a big gap where the N2O4 used to be. How can it replace the N2O4? Shift left or shift right? It's going to shift to the left. Right? If I remove a reactant, it's going to try to replace it by shifting to the left. If I do the opposite, I come over here and I remove a product. Oh, wow, that was a big gaping hole where the NO2 used to be. How can it replace it? Shift to the right. That makes sense? Okay, so you read some of that in your pre-lab, hopefully, for today. Just talking about some of this stuff. Okay, how about changes in temperature? Well, we've seen that reactions can be, I believe we did. Yeah, way back chapter 5. They can be exothermic or endothermic. Remember, exothermic means it gets hot and it releases heat. Endothermic means it gets cold and it absorbs heat. So if something is exothermic, it's releasing heat. That basically means you can think of heat as being a product. So I actually went ahead and actually wrote heat over here on the product side. So if it's getting hot, it's producing heat. So heat is a product, right? So let's say I have that reaction, and it's exothermic, I know, and I come along and I put a Bunsen burner under it, and we get to heat it up. So now I'm adding in heat. Well, I'm basically adding in a product. What can the reaction do then to try to get rid of this extra heat that I'm pumping in? Has to shift to the left, and that uses up the heat and turns it back into N2 and H2. Does that make sense? Are you sure? Okay. Okay, how about the opposite? How about I come in here and I put this whole beaker in a test tube, and a bunch of ice, and I cool it off, and I begin to remove the heat. What's it going to do? How can it replace the missing heat now? It's going to shift to the right. Right? Okay. What if it wasn't exothermic? What if it was endothermic? Well, endothermic means it absorbs heat. So heat is basically a reactant now. So I write plus heat on the reactant side. So now I come along to this thing, and now I put a Bunsen burner under it. And I heat it up, and I begin to pump in heat. How's it going to react? What's it going to do? Shift left, shift right, or nothing? Just deal with it. Oh, well, if I add a bunch of extra heat, the way to use up the extra heat is to go to the right and use it up, right? So we shift to the right. Yes. And vice versa, if I were to take it and I were to put it in ice, right? And I were to suddenly remove the heat. Oh, well, okay. What's it going to do? How can I replace the missing heat now? Shift left, right? So go back this way and produce heat to replace the missing component there. Okay, so we discussed adding reactants or products, removing reactants or products, adding heat, removing heat. The last we're going to look at is volume and pressure. So, now this is only for gases. So if you increase the pressure, the reaction is going to shift to whichever side has fewer gas molecules. Not aqueous, solid, or liquid. Gas molecules. That's the key component there. So, if I increase the pressure, I'm going to go towards the side that has the fewer gas molecules, and vice versa. If I decrease the pressure, I'm going to the side that has more moles of gas. So how can I change pressure? Well, the easiest way is just to change the volume of the container. We saw this before back in chapter 8, I think it was. Right? So as volume decreases, pressure does what? Increases. And as volume increases, pressure decreases. So we can do that as well with a reaction. So let's just look at an example here. Let's say I have this reaction. N2 plus 3H2 is equilibrium with 2NH3. So I have it. It's nice and happy. It has an equilibrium. Then I come along and I squeeze it down tighter. So the volume went down, which means the pressure went what? Up. Okay, so I had it, it was all happy, and now it's like, ugh, too much pressure, right? It's all compressed and compact, and it can't deal with it. Well, how can it then begin to relieve the pressure? Well, if it goes this way, it takes 2 moles of gas and doubles them into 4 moles of gas. So that's going to make more pressure, right? If I go this way, I take 4 moles of gas and convert them into 2 moles of gas. So that will be fewer molecules, so that would relieve the pressure. Does that make sense? So if the volume goes down, the pressure goes up, what can it do? Shift to whichever side has fewer moles of gas. Again, only count the gas ones. Don't count solids, liquids, or aqueous. So here I see 1 and 3, 4 moles of gas. Here I see 2 moles of gas. So in this case, if I decrease the pressure, what's it going to do? Decrease the volume, increase the pressure. It's going to shift to the right. It's going to take 4 moles, and turn them into 2, and 4 into 2, and 4 into 2, and 4 into 2, until it gets back to a nice happy pressure. That's going to lower the pressure, right? And the opposite's also true. If I were to take that same thing and I were to suddenly take it and make it a lot bigger, now it's like, whoa, there's way too much space around here, right? Because how can it increase the pressure? It's the opposite. Go to the side that has more moles of gas, right? So take 2, make 4. Take 2 and make 4, and that'll get the pressure back up to where it wants to be. Does that kind of make sense? Kind of? No? Ask me questions. Okay. Well, let's try it. This is the last 2 slides. So you have 2HI goes to H2 and I2. I come into here, and I pump in a bunch of extra hydrogen. What can it do? Shift left, shift right, or will it have no effect whatsoever? Okay, if I add in a bunch of extra product, how can it use it up? Yes, shifts to the left. Okay, I come in here now, and I begin to remove the iodine. I begin to suck out the iodine. How can it replace the missing iodine? Yes, shifts to the right. Okay? I come in here, and I begin to remove HI. So that's going to shift to the left again, right? It's going to replace the missing HI. So I have this volume, this container, this balloon, whatever it is, and I double the size of it. So the volume got bigger, means the pressure did what? Pressure went down. So how can I increase the pressure? How many moles of gas are on the left?
2.
How many moles of gas are on the right?
4.
How many moles of gas are on the right? 2. I just see 1 and 1, 2. So there's not a darn thing you can do about it, right? Because it doesn't matter. There's 2 on the left, there's 2 on the right, right? So it doesn't matter which way it goes. You can't turn 2 into 3 or 2 into 4 and get it back, right? So that would have no effect. Nothing happens on that one. Can't do anything about it. Okay, it says the reaction was exothermic, which means heat's a reactant or a product. Which one? Okay. Heat is a product. So I'm going to go ahead and just run, just to remind us. Plus, try a different pen. Plus heat. Right, exothermic means plus heat. So the temperature is decreased, so I cool it off. Left or right?
Right.
So I basically removed the heat, so it's going to go to the right. Okay? Question, yeah.
Okay, so let's say the volume of the container was doubled.
Uh-huh.
Can't do anything. If the volume of that same container was like
Shrunk?
shrunk down.
Yeah, same thing. Still can't do anything. There's no way it can either make more or less molecules. Yeah, there's nothing you can do about it.
But so if that was cold, the heat would still be on the right side?
Yeah, it doesn't matter because it's exothermic, it says. Yeah, right. Exothermic tells me heat's a product.
So if it was boiled, then it would be on the left side?
If it was endothermic,
Yeah.
boiling doesn't really tell me anything about the reaction. I mean, boil just means heat was added. It doesn't necessarily tell me if the reaction itself produces heat or the reaction itself actually requires heat. That doesn't really tell me about that. Okay, last one will be done. So your turn. Take your 4 guesses. Talk it over when you get your 4 guesses. I think this is the last slide, right? Oh, I lied. It's next to last slide. Okay, so you have 4 guesses. Okay, discuss. Talk it over with somebody. Shift left, shift right, no effect. Talk it over with somebody. If you're not sure, really discuss it. It's like, I don't know, what do you think? Okay, so I come in and I remove water. What's it going to do? To the left, to the left. Okay, it's going. Okay, I come in and I increase the temperature.
Right.
Okay, why is it to the right for this one?
It's an endothermic.
Okay, it told me it was endothermic, which means heat is a reactant. So if I add in extra heat, it's got to shift to the right. I come in and I begin to remove CO. Left, right, or nothing I can do about it. Okay. If I remove CO, that was a big gaping hole where it used to be. What's it going to do? To the right. Has to go to the right to make more CO. Okay. The volume gets 3 times bigger. So if the volume goes up, the pressure did what?
Went down.
Pressure went down. So, okay, the pressure is too low. So if I want to build back the pressure, I need more molecules. Which side has more moles of gas? Yes, this side has 2 moles of gas, right? 1 and 1. This side has 1 plus 3, 4 moles. So yes, it would shift to the right. Okay, well, I'm going to take this another couple of minutes. Somebody's in here after us, and we have lab. Just to do this last one, because I want to point out, come here, it's kind of special on this one. And I'll give you a 10-minute break still, but just had it start 5 minutes late. But so just try this one, because it's a couple of these are a little sneaky. So left, right, or no effect. So just think about these 4 and then talk about it. Okay. I'll go over. So the first one, if I remove carbon, left, right, or no effect?
No effect.
Actually, it's no effect. Why is it no effect?
This is solid.
Because it's a solid. So again, the solids don't appear in the expression. So again, it doesn't matter if you have a lot of it, little of it. It doesn't matter. So it actually has no effect for that one. So that one's a little sneaky. No effect. Because again, solids have no effect on the equilibrium. Neither do liquids, right? The volume of the container is had, so it gets smaller, which means the pressure goes up. What can it do about it? Wrong. Count moles of gas. Moles of gas. Don't count solid. The left side has how many moles of gas? 1 mole of gas. The right side has 2 moles of gas. So the pressure went up. So how can it remove the pressure? To the left. Turn 2 into 1. Turn 2 into 1. Turn 2 into 1. Carbon monoxide is added. To the left. Temperature is decreased. Okay, it tells me it is endothermic, which means heat is a product. So if I remove heat's a reactant. So if I remove heat, it has to go to the left then to try to replace it. Yes. Yay, a whole chapter in one lecture. Awesome. Okay, well, I'll see you in 10 minutes. So whatever that is, 3:36.